My name is Amit Silami and I'm a PhD candidate at the College of William and Mary, United States of America. In this video, I'll be demonstrating MUSE, Mutation-based evaluation of security-focused static analysis tools for Android. Mutation testing is generally used by software practitioners to assess the robustness of a given test suite. However, we leverage this technique to systematically evaluate static analysis tools to uncover and document soundness issues. There are three distinct phases of this semi-automatic approach. At first, we define security operators based on security goals instead of tool-specific properties. As a result, entire classes of tools can be analyzed using the same security operator. The effectiveness of these operators in finding unsound assumptions is enhanced through the introduction of mutation schemes, strategies that define where to apply security operators to seed mutants in applications. Once these are specified, MUSE starts by analyzing the given project to identify the application Java source files while creating a model based on the Eclipse Abstract Syntax Tree framework. Based on the selected mutation scheme, MUSE identifies locations where security operators can be injected. When all these locations are identified, the security operators are introduced. Mutations are inserted and checked for syntax issues through Java compiler diagnostics to kill error-prone mutations preemptively. Furthermore, the mutated applications can be optionally executed by an execution engine, for example by crash scope, to filter sourcing type mutations which may not result in data leaks. The analysis of SUSPs is done manually by applying them to detect mutants. Logs of results from tool analysis and inserted mutations are then compared to understand what mutations were not detected by the tools. Finally, undetected mutations are analyzed to determine soundness issues in these tools. Note that the specification and mutation phase are done only once for a family of tools, whereas the analysis has to be done on a per tool basis. Following this methodology, we were able to find 25 previously undocumented flaws in Android data leak detectors. Now I will demonstrate how MUSE is used. MUSE offers both command line interface and graphical user interface. Both versions can be executed while specifying a properties file. You can use an already existing properties file or generate one from the graphical user interface. To do so, you need to specify the name for saving the file, the path to necessary AST libraries, path of the base Android application which will be mutated, and the mutation scheme. Additionally, you need to specify the destination at which the mutated application will be exported. Then, when you execute MUSE, it will create mutation as well as produce logs which describes the locations of mutations. You can also save the mutation log for later use. As you can see, the properties files are of course editable via text editors. Let's take a look at a sample application and how MUSE mutates it. It's a rather simple class with nested classes and a few methods. By applying the reachability scheme, we place data leak mutations in all reachable locations. The end result is like this. On the other hand, ChainSync mutation scheme aids in evaluating tools by placing the source and sink in different locations that can be called asynchronously. For example, some methods are automatically called due to Android lifecycle methods, and some methods might be invoked depending on user interactions. In this type of scenario, depending on the order of method calls, a sink may or may not leak sensitive information. MUSE also has scope sync mutation scheme, which considers visibility scope from object-oriented programming paradigm for introducing source and sinks in different locations. This concludes our demonstration of MUSE. The tool is open source. If you're interested, you can find further information in muse-security-evaluation.github.io. Thank you for your time.